Good morning. My name is Peter Shields and I'm pleased to welcome you all to today's webinar, Reliable Dust Measurements and Nephelometer Data Processing. This morning we're fortunate to have Dr John Wagner, the Global Training and Support Manager from Aeroqual in New Zealand, to present on this topic. John has vast experience in this area and I'm sure you'll find him interesting and informative. I'll now hand over to Dr John Wagner, who's kindly agreed to present from New Zealand today. So thanks, John. Over to you.
Thank you, Peter. A little bit about myself. I work with Aeroqual Limited. We are a manufacturer of air quality instrumentation. My role as a training manager is to provide training and support to our global distribution network. Dust monitors, or sometimes referred to as particulate monitors, form a significant portion of our business and what we manufacture. And I thought I'd talk to you a little bit today generally around some dust monitoring concepts and terminology. Talk to you a little bit about what kind of instrumentation is available to us for measuring dust. Some of the key points to understand about the different types of instrumentation and why we may select one over the other. Talk to you a little bit about sighting instruments for reliable dust measurement and understanding some of the limitations of some dust monitors and how we can overcome those. And then towards the end of the presentation, I'll be talking to you a little bit about data processing from dust monitors and common and popular ways of presenting some of the data that are generated from dust monitors. To begin the presentation, I thought I'd talk to you a little bit about some terminology. In the dust monitoring world, the terminology can be quite varied. Most governing bodies, national standards bodies, including the Australian standards bodies, the American standards, and the European standards are beginning to tighten terminology and the definitions of those terminology. So it's a good question, I think. What is dust? Obviously, dust means different things to different people. Dust can be, anything ranging from very heavy airborne particulates to much lighter airborne particulates. One of the key things to understand about particle matter terminology is that the size of the particulate matter is very important in regards to both the choice of instrumentation to measure and the impact that that dust has on the public and on the environment. So again, what is dust? Well, dust is not particularly well defined in the legislation. Dust is a broad term and it refers to any airborne particulate. It's not a very well-defined term. To give you some idea of the kind of sizes of particulates that would be covered under the term dust, usually the particulate size can be anything from 75 micrometers in diameter or anything up to 100. So I've given you two different, in fact, definitions of dust. One comes from the International Standards Organization and the other one comes from the Glossary of Atmospheric Chemistry. I put these up only to give you an indication that the terminology of dust is not particularly well defined or agreed upon. You may hear another term which is often used in place of dust, and that term is TSP, or Total Suspended Particulate. Several years ago, during the 1980s and the 1990s, the legislation included this term, Total Suspended Particulate. And although the definition was not well defined, often the term Total Suspended Particulate referred to those particles below 75 nanometers in diameter. So that gives you some idea of how the terminology is set. In more recent times, the terminology has changed and a more strict definition has been put around the phrasing for particulate matter. And we tend to hear the terminology PM10 or particulate matter 10 or particulate matter 2.5. The 10 refers to 10 microns and the 2.5 refers to 2.5 microns. And this image gives you some idea relative to a human hair of the kind of sizes that we're referring to. So why do we have these different terms? And more importantly, why is the terminology and the focus changing? So as I said, during the 1980s and the 1970s, dust, or TSP, was regulated nationally by both the Australian government, the United States government, and also the European government. However, it soon became apparent that regulating dust was not a particularly useful pollutant because the impacts on human health of dust were not very well defined. More recently, dust is beginning to be referred to as a nuisance rather than a health risk. This is because particle matter larger than PM10 does not tend to penetrate the lungs. It gets caught in the nasal cavity and perhaps in the back of the throat. In terms of population health, this is not considered to be high risk. Therefore, dust as a pollutant tends not to be regulated by national standards because it isn't really considered to be a health risk. PM10, on the other hand, particle matter of 10 microns, is a health risk because particle matter of this size can penetrate the lungs. And even worse, particle matter of the smaller size fraction is an even more serious risk because of the depth of penetration into the lungs. Again, because of these health risks associated with the smaller particle sizes, PM10 and PM2.5 are regulated nationally through an Act of Parliament. This is true for New Zealand, for Australia, for the European Environment Agency, and for the US EPA. On the other hand, dust does not receive the degree of regulation that the smaller size fractions do. Now, this is different in different countries and different regions, but generally speaking, dust tends to be regulated by local rules and regulations, municipal rules and regulations. Dust is often regulated in a similar way to noise control. Some industries, construction industries or demolition industries, will regulate themselves through best practice guidelines, and some local governments publish what might be called guidance documents on the regulation of dust. Okay, so one more time, the particulate matter PM10 and PM2.5 are universally defined. They have a very strict definition, and that definition relates to their size. PM10 pollution is all particles of size 10 micron and below. PM2.5 refers to all particles of PM2.5 and below. And not only are these definitions more universally defined, but this type of particle pollution is regulated. So the key concept here really is that the different particle sizes, dust, PM10 or PM2.5, are considered very differently. So this is an excerpt from the Australian National Standards for Criteria Air Pollutants. These are very similar to what you would see in the US EPA or in the European Environment Agency. So just notice that in the national air quality standards, as well as pollution gases such as carbon monoxide and NO2, we see particles as PM10 and particles as PM2.5 are regulated at the national level. And they give us what they call exposure limits. For PM10, the exposure limits are set at 50 micrograms per cubic meter, and particles as PM2.5 are set at 25 micrograms per cubic meter. The key point here I just want to emphasize again is that dust is not mentioned in the Australian national standards, nor is it mentioned in any other international standard. And this is because dust is considered to be a public nuisance rather than a health risk. So as dust is not generally regulated at the national level, questions arise as to how is it often regulated and how are dust emissions controlled, and how are users encouraged to control dust emissions, monitor dust emissions, and report on dust emissions. So this type of guidance often comes in the form of either a best practice guide written by industry or sometimes it comes in the form of a guidance document written by a local municipal government. One particularly useful document is the Guidance on Air Quality Monitoring in the Vicinity of Demolition and Construction Sites. This is written by a UK authority. I'll be referring back to this document in later parts of the presentation. But the UK government is not the only not the only publisher of guidance documents. The Australian government, or in this case the Western Australia government, also produces what they refer to as guidance documents. Note just one more time that this is not regulatory information rather than guidance. So what are the sources of dust and what are the sources of particulate matter? Dust is usually caused by some kind of mechanical action. It can be grinding, crushing, such as you might find at a quarry. Very often it's vehicle movement on unsealed roads which causes dust emissions. PM10, on the other hand, is usually often caused by burning of some kind of fossil fuel. And PM2.5 is also combustion related, but it tends to be associated with traffic emissions. Dust monitoring often is a short-term activity and related to a specific activity in a well-defined area, such as a mine or a building site. And the monitoring, dust monitoring, that is often carried out by whoever is actually causing the dust emissions. Remember again that dust is not regulated nationally. PM10 and PM2.5, on the other hand, the monitoring of PM10 and PM2.5, because of the health risks, are often performed by local government, municipalities. PM10 and PM2.5 monitoring often form part of a regional network of monitoring apparatus which operates year on year, but is not related to any particular activity or project. So moving on, how do we actually measure dust? What are the tools available to us for measuring dust? Well, there are many. There are many instruments which can measure dust. Most of those instruments tend to focus their measurement on either PM10 or PM2.5. The most accurate and the most historical reliable measurement is what's referred to as a gravimetric high vol. This is rather a large instrument. It stands approximately 5 feet tall, and the way this particular instrument works is it simply sucks dust particles onto a filter with a very well-defined flow rate of air, and that filter paper later is weighed very accurately, and this gives rise to a mass of particulate matter captured over a given time period. This high vol method is often referred to as a reference method. This method is prescribed in the Australian standards for PM10 and PM2.5, and it's indeed prescribed around the world as being the reference standard for PM10 measurement and PM2.5 measurement. One of the disadvantages to the gravimetric high vol method is that it's not real time. So typically sample periods for the gravimetric high vol are around 24 or 48 hours, depending upon the site. These are used in national air quality monitoring networks. So although they give a very accurate reading, what they do not allow us to see are what you might refer to as emission events. These are short-lived, high concentration emissions of dust, or PM10. Rather, they integrate over a fixed period of time. Another level of instrument accuracy are what's called the equivalence methods. Now, this word equivalence is well defined and well prescribed within the standards, and simply refers to a degree of accuracy and uncertainty relative to the reference method. So the reference method is considered to be error-free. It's considered to have zero uncertainty, and then the equivalence methods are assessed relative to the reference method. The equivalence methods offer us some advantage over and above the reference method. Some of the key advantages of the equivalence methods is that they are semi-real time, which means that the sampling period can become as low as 15 minutes or quarter of an hour. And this allows us to see over the course of a single day how the dust emissions, or the PM10 and 2.5 emissions, are changing with time. The disadvantages to these three methods, the gravimetric high vol and the two equivalence methods, is that they're all expensive to purchase and expensive to operate. Two equivalence methods require sheltering from the weather. They don't come IP rated, and it takes a high degree of operator experience to get good data, often from the equivalence methods. But if you are monitoring for compliance reasons, which means if you are a municipality and you are forced to monitor air quality through the Clean Air Act, then you are restricted to using only these reference or equivalence methods because of their known performance and accuracy. And again, I should point out that these instruments are typically designed to measure PM10 and PM2.5. So they have what is called a size selection mechanisms. Some of those mechanisms are physical, others are different. But when it comes to dust or TSP, we have other options. Again, because the dust monitoring is not regulated under the national standards, we have the freedom to explore other measurement types. The dust monitors tend to be what's called an optical measurement. Optical measurements, we'll look at a little bit later how they work. But they work differently than the gravimetric method and differently than the two equivalence methods. And the key benefit to the optical methods is that they are very real time, which means they can provide data at 1 minute intervals. The technology is generally cheaper to purchase and cheaper to run in comparison to the equivalence methods. But there is a corresponding sacrifice in data quality. And we'll be talking a little bit later about how we can mitigate some of those issues. This is a table which has been taken from the UK guideline document on dust monitoring. But this gives you a really good rundown on the different types of instrument available for measuring dust and some of the advantages and disadvantages of the different methods. The two equivalence methods are what are the tapered element oscillating microbalance, or commonly referred to as a TEOM, and the beta attenuation monitor, commonly referred to as a BAM. These two instrument categories are listed on the left-hand table under TEOM analyzer and under the beta attenuation analyzer. The filter-based gravimetric samplers are listed on the right-hand side, and the optical analyzers are shown as a technique on the top line of the right-hand table. So just to put things in perspective around cost and data accuracy. So the high-vol systems and another gravimetric method, often referred to as a partisol, these are certified instruments and certified for use in national monitoring networks. They come at very high cost, both cost to purchase and cost to run, but the data quality is very high. One level down, often referred to as a certified equivalence method, are the TEOM, the MET1 BAM, and the GRIM. Again, these are often used in compliance monitoring networks to meet national standards for PM10 and PM2.5. Just recently, the UK government, or I should say the European agency, have defined what they refer to as an indicative standard. So this is a lower level or a high level of uncertainty, a lower level of accuracy, and this indicative standard is given to dust monitoring only, and it means that the lower cost instruments, the cheaper to run, cheaper to purchase instruments, do actually need to qualify under a performance standard, and that performance standard is called MCERTS, which I'll refer to a little bit later. I should also point out that the optical instruments, although are more commonly used for dust monitoring, can actually be made to measure PM10 and PM2.5. So just going back to our original document, I'd just like to have a look at some of the advantages and disadvantages of the different techniques. So if I'd just like to draw your attention to this section, This covers some of the advantages and disadvantages of the optical analyzers. The key advantage to the optical techniques is that they can be easily deployed. They're lightweight, portable, low power, and they're real-time. That real-time measurement is a key advantage of the optical techniques because it allows site managers, environmental managers to react quickly to short-lived particulate emissions. And one typical example of this is to use the instrument measurement to trigger a sprinkler in order to suppress dust emissions from a road. But if you look at some of the other instruments, again, if we consider the T-ohm, which is, if you remember, an equivalence method, because these instruments are typically used for long-term municipal monitoring networks, they're less suitable for using in construction sites and demolition sites and mines. The disadvantages here, I mean, they're high capital cost and high operational cost, and do require careful servicing and maintenance. And that's the same for the beta attenuation monitors. Also, the gravimetric filter samplers listed here, although are incredibly accurate, considerable experience and care needs to be taken in their operation. So I thought what I'd do now is I'd have a look at the two most common optical techniques. There are two common techniques available. One technique is often referred to as particle counting, and the other technique is often referred to as nephelometry. So I've tried to put together an animation here on the screen which gives you an idea of how the particle counters work, and then in the next slide we'll have a little look at how the nephelometers tend to work. So with particle counting and nephelometry, in fact, the particles are made to pass through a collimated laser beam. That laser beam shines directly into a light trap which captures and absorbs the laser light. With the particle counter technology, when a particle falls through the laser beam, it scatters the light. That scattered light is collected by a front surface mirror, and that front surface mirror then focuses that scattered light onto a light detector, and that light detector measures the collected light. There are two properties of the light which we are interested in. The particle counting comes from an individual pulse of light which is caused by a single particle falling through the laser. So this is how particles are counted. The pulses of the laser light shining onto the collector are counted. The size of the particle, that is whether the particle is a PM10 particle or a larger particle or a smaller particle, is defined by the intensity of the light which is reaching the detector. So this method is particularly economical because it means that we can measure TSP or dust, PM10, PM2.5 or PM1, which is a much smaller fraction, simultaneously, all at the same time. A mathematical formula allows us to convert from the particle counts into particle mass in micrograms per cubic meter. And so the data looks very much like the graph on the bottom right-hand side of the screen, where over time we have a measurement of TSP, a measurement of PM10, 2.5 and PM1. This graph illustrates a key concept, of course, around particle terminology, which is that TSP refers to all particle sizes, that is every particle we can measure, or dust. PM10 refers to only particles of size PM10 and below. PM2.5 refers to only particles of size PM2.5 and below. So of course we will always expect our dust measurement or TSP to be higher than PM10, which should likewise be higher than 2.5 and higher than 1. So this is one method. This is the optical counting method. Now it is the method of highest uncertainty or lowest accuracy of the two optical methods. And the reason for this is because the integrity of the front surface mirror can degrade over time, and this can significantly affect not only the counting but the binning, the size binning. So particle counting with mass conversion tends to be used as a survey tool for very, very quick dust assessment, and doesn't tend to be used for a longer-term monitoring strategy. Another method is nephelometry. So nephelometry is the only certified optical technique, the only method which has actually achieved indicative certification. So this works a little bit differently than the particle counting. The key difference with nephelometry is that the particle size, so TSP or dust, or PM10 or 2.5 or 1, the size is selected mechanically through the use of a particular size selection cyclone. Cyclone is what you can see in the image in the top left-hand corner. It's a mechanical aluminium cylinder whereby particles are made to turn very, very fast, a little bit like a Dyson vacuum cleaner. And particles of which are too big do not make it around the cyclone and are spat out on the side. Those particles which are small enough or which qualify as PM10 or 2.5 are sent down to the optical chamber. Note that when we measure dust, because dust is everything, we don't have the size selection cyclone. So when we are operating an instrument based on nephelometry, we simply have a TSP head, that's the white head. But if we're interested in measuring PM, then we would need to put a size selection filter. The method, so once we've selected the size, the method is similar to the particle counting in that we are relying upon scattering of light. The only difference here is that the optical configuration is linear, it's all in one line. The laser is made to shine into a light trap, similar to the particle counter, but when the particles fall through the laser beam, the light is forward scattered, and often you hear the terminology forward scattering nephelometry. And that forward scattered light is collected by focusing optics and is then focused down onto a light detector. So as the light detector picks up that scattered light, we see that we get a measurement in particle concentration in micrograms per cubic meter. The real-time nature, I guess, is illustrated here in the animation. We don't have to wait to accumulate particles either on a filter or on a balance in order to get a measurement. The measurement comes immediately in real time. At this point, it's a good idea perhaps for me to just reference one of the limitations of the optical methods. So as the illustration I've showed you, I haven't really talked about what the particle matter is, but one can visualize what might be happening to particles of different colors or opacities or even morphologies as they fall through the laser beam. So to give you an example, if we're trying to measure particles of mass PM10, particles of size PM10, we are making some assumptions when we're using an optical method. And one of those assumptions is that the particle which is falling through the laser beam is of a particular color and is perfectly spherical. This is obviously not a realistic assumption, but it's the only assumption that we can make. But you can imagine that if the particles are made from soot, from carbon, they will have a different interaction with the laser beam than particles which are made from clay or from iron ore or sea spray, salt. So keep this limitation in mind, and then we will come back to ways of mitigating that. I'm only going to mention once on one slide about monitor placement. There's a really good Australian-New Zealand standard which talks about siting air quality monitoring equipment. Where you choose to place a monitor is going to depend a lot upon the monitoring application. Again, for municipal PM10 and 2.5 networks, instruments tend to be placed strategically throughout a region. Some monitors are considered background monitors, so they will be placed in areas of minimal human population, so we can understand what the background levels are. And some might be placed among high population density areas like central cities or areas where there are lots of people. For point source or dust monitoring, such as a building site or mine, Instruments are typically positioned on the boundary between the site where the dust is being generated and neighbouring communities or sensitive communities. One trend that we are observing overseas, a common approach, is to use 3 instruments placed at 120 degrees apart. This is to allow for measurements to be taken regardless of the wind direction, and it also helps site managers understand what the contribution is to dust from activities not related to them. So as the wind direction changes, they can get their own background measurement. So I would refer you to this document for guidance around monitor placement. Okay, so I'd like to come back to this idea of what a lower accuracy or higher uncertainty method is relative to the reference method. With the gravimetric reference methods, the particulate matter is collected and weighed directly. So because particle matter concentrations are referred to as weight by unit volume, weighing the accumulated particle matter is the most accurate method. And because we are weighing the particle matter, the morphology or the composition of the particle matter is not going to affect the mass measurement. So it makes no difference whether we're weighing carbon, soot, or sea spray, or anything, or silica. With the optical method, because we're relying upon an interaction with the particle with a laser beam, the shape, the morphology can affect the accuracy of the measurement. And this is why the optical methods are often referred to as indicative, because of this inherent lack of accuracy or inherent uncertainty associated with particle type. This disadvantage is highlighted in the guidance document I showed you previously in the UK. The disadvantage is described here, that the calculation, and notice this is calculation of PM concentrations, because it's not a direct measurement of mass. So we are calculating mass based on a laser interaction. They say that the calculation of PM concentrations are based upon assumptions about particle characteristics, which may vary from place to place and from time to time, and may be subject to artifacts. So what they are referring to here is that if your instrument is placed in one location and it's measuring silica dust, and it's placed in another location and it's made to measure a carbon dust, the instrument is going to respond differently. So this is really what it means. So how do we get around this problem? How do we improve upon the accuracy of our optical method, given all of the advantages it has? That is the real time, the low cost, the ease of deployment. How can we mitigate some of the disadvantages? So the most common way of doing this is to actually operate the optical method side by side, or we call collocation, with a more accurate measurement, a more accurate instrument. So either the gravimetric measurement or one of the indicative measurements. Typically, we would do a collocation correction for maybe 1 week or possibly 2 weeks if we can afford the time. We would then take the measurement from the more accurate instrument, such as the high vol, and we would use that and compare it to the measurements obtained from the nephelometer, from the indicative instrument, and we would apply what's called a K factor, or sometimes referred to as a correction factor, and this adjusts or corrects for differences in response for the different particle types. So as long as the instrument remains in place, or at least as long as it is made to measure a similar particle morphology, then this correction can dramatically increase the accuracy of the nephelometer method. Another way, a slightly less common way, but another method, if a user does not have access to an external high-vol sampler, some instruments, some nephelometer instruments actually have sample filters built in. This is an example up here. In this example, the real-time optical measurement is made in the top right-hand corner of the instrument. So this is a nephelometer. So the nephelometer provides the real-time fast response with all of its uncertainty or inaccuracy. Then those particles are actually collected on a sample filter in a similar way to what they would be for a high vol, except that in this case the volume of sampled air is much lower. However, it's still possible in some cases to use this collection filter. The instrument can be operated for a period of, say, 48 or 72 hours, and the real-time measurement, real-time optical measurement, can be compared to the mass of particles collected on the sample filter, and then for that particular monitoring location, or even that particular monitoring project, a correction factor can be applied. And this dramatically mitigates the effects associated with morphology and particle type. So I'm not going to dwell too much on all these numbers, only to let you into a sort of a not very well discussed secret in dust or even air quality monitoring data. Often when we are presenting particle data, we present averages, so a daily average or an hourly average. This is really, really common. This works really well for most measurement types. So if you see in the second column, PM10, I've averaged those values over a very short period of time, just to give you an idea. And the averages work quite well. This averaging is common, and it works very well for all types of data except for wind direction. Wind direction is a slightly different type of data structure than wind speed or particle type, because wind direction is discontinuous. So what that means is that wind direction doesn't go on forever. There's a discontinuity around the northerly. So when the wind blows from the north, it's a common error in air quality data processing to provide a wind direction average. And if you look at the data I've shown you there for wind direction, if this data is averaged, it leads to an error, quite a dramatic error, in fact. And in many cases, when wind direction blows from the north, subsequent data processing ends up looking like data blowing from the south. So that's a well-known problem with wind direction data processing. The solution is not too complicated. It depends how comfortable you feel with trigonometry. I'm not going to bore you too much and go through the process. There is a solution, and any good quality environmental data processing software deals with this without too many problems. It basically involves converting the wind direction into an alternative coordinate space, and executing the average on that coordinate space, and then converting back to degrees. So just to let everybody in on that little secret that sometimes this error can occur. But what about actually presenting concentration data? So I'll start to talk. I'll mention first of all a windrose. A windrose is a really very common way of presenting wind speed and direction data. Windroses are typically presented as a compass image with a north, east, south and west, and the intensity of the wind is often given by colour, and the abundance of wind from a particular direction is usually given by the distance from the centre. So if you look at this particular diagram, this will be the windrose for, say, a particular date and time. This one is for the 5th of May. The wind starts, the majority of the wind blows from the southwest, but when it does, it's not very strong. A smaller portion of wind blows from the south, and when it does, it blows stronger from the south. So that's how we would interpret that windrose. The concept of a windrose is expanded, and often we produce what's called a pollution rose. So a pollution rose tells a good story, tells you from where is the pollution coming from, and how much, and over a particular period, where is the majority of the pollution coming from. So you can imagine a situation where we might have an industrial situation like a coal-fired power station next door to a residential area. It would be common to place a dust monitor with additional wind speed and direction on the boundary between the residential area and the power station, and then to measure the PM10 concentrations or dust, depending on what the objective is, and also to measure wind speed and direction. What this allows us to do is to present a story or to present data in a fairly easy to understand way. And if you look at the pollution rose here, this pollution rose tells you that most of the wind for the 5th of May came from the northeast. That's the abundance of wind coming from the northeast. When wind blew from the northeast, the particle concentration was relatively low, probably below 20. For a smaller portion of time, the wind blew from the southwest, but when it did, the concentration of particulate matter was higher, and obviously that's where the coal-fired power station is. So that gives you an idea of how to easily present PM10 data based upon wind direction. There's an abundance of software available in the market which makes presenting these wind rose plots and pollution rose plots quite easy. There's a free tool available called WinRAR Plot. This was actually originally developed by the US EPA, but it's now distributed by Lakes Environmental, who are a very well-known environmental software company. This is freeware. There's also an open source package called the Open Air project, just based all on open source code. And actually, if you want my opinion, I think it's a much better package and really produces very high quality and easy to edit images around and diagrams to present pollution data. So just a very quick note about Aeroqual. We manufacture a range of dust instruments. We produce one instrument called a dust sentry. The dust sentry is a certified instrument for measuring PM10, but can also measure TSP or dust. It has a European performance certification. The performance certification is MCerts, and it's the only certification worldwide for indicative ambient particulate monitors. All the other certifications relate back to the certified reference and indicative monitors, which we spoke about earlier. The instrument is fairly small. Again, you can see it's fairly easy to deploy. It's low cost, low power, and can include weather sensors as optional, inclusive of the PM measurement. The software runs on any platform. It's not required PC desktop software. The software is operated through a browser. It's cloud-based software, or it can be device-based software, and it can be used on a tablet, on a PC, on a smartphone, Apple, Safari, or Chrome, or whatever your browser is of choice. And we can also set up data can be emailed to you, or you can receive text alerts for exceedances using the cloud-based software. All of these documents, I hope, will be available to you at the end of the seminar. I highly recommend the guidance documents published out of the UK. They're very high quality and very well thought through. And in fact, the UK is probably leading the world at the moment in discussing the mitigation, monitoring of dust, especially around urban sites for demolition and construction. By all means, refer to your own documentation. The Western Australian government produced a good guideline document on the implementation of a dust measurement program. And on the Aeroqual website, there's a few case studies around the use of our own real-time dust monitors in quarries and construction sites.
I'd just like to thank you all for attending today. I trust you found it useful and interesting. As a follow-up, we'll be sending out an email next week that will have a link to the recording of today's presentation and all the reference material from the presentation. So those things that John referred to, we will have links to those on the follow-up email. AirMet represents the Aeroqual product range in Australia, so if you'd like any further information on these products, please feel free to contact us. And finally, I'd just like to thank you, John, for your time today. Very informative and interesting presentation, and I really appreciate the effort that you went to. So thanks very much.
Thanks, Peter.